Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. This video will be looking at fugacity of species in a mixture by phase. Our goal is that you should be able to write an expression for evaluating the fugacity of a species in either a gaseous mixture, liquid mixture, or a solid mixture. So for gases, let's start by looking at our definitions for fugacity of a species in a mixture and compare that to the fugacity for the pure substance. They're very similar relationships, and in fact, we frequently are able to relate these two to each other. Now, we can often estimate that the mixture is essentially an ideal mixture, and relationships for ideal mixtures are written here for volume and for the Z, the compressibility factor. If we do that, then the partial molar volume is the volume of the pure species, and therefore the fugacity for the substance in a mixture for a gas is equal to the mole fraction times the fugacity of the pure substance as a gas. This is called the Lewis-Randall rule, and it actually is frequently a reasonable first estimate, especially if all you're trying to do is a rough approximation so that you can compare your answer to a more rigorous calculation done, say, in a computer program. If you want to be a bit more rigorous, then we should probably use a model for the pressure, volume, and temperature relationship, an equation of state. Unfortunately, these are best written as pressure as a function of temperature and volume. It's generally very difficult to solve for the volume as an explicit expression. So therefore, it's easier to work with this as an integral of how things change with volume. And going through Jacobians, you can get to this expression here. This says that I can estimate this for a function of p of t and v using yip, the exponential, and I'm going to go from, instead of p equal to 0, I'm going to go from v equal to infinity. It's the same point, okay, just a different expression of that point, up to the actual volume. And I'm going to integrate the pressure expression, okay, RT over V for the ideal gas minus what it would be for this species in a mixture. Integrate that over the volume, and then I need to subtract off the natural log of the compressibility factor for the vapor phase. Now, if you choose to use a virial equation, just using the single first term, then we end up with this expression here. Now, this doesn't look any different than it would for a pure species, except for that B needs to reflect the mixture. And the way we do that is we add up these B's that are determined based on statistical mechanics, maybe simulations, for when I have a combination of any two molecules together. And we're going to do that for the relative Y values of the various substances. And I need to do this for every possible binary combination. That gives me this as my final expression, where the Z for the mixture is 1/2 1 plus the square root of 1 plus 4 times the B for the mixture times P over RT. And so this becomes a way of estimating the fugacities if I have the B's for all of my binary combinations. We also can do this with any of those cubic equations of state. In the textbook, they show you the equation for the multi-component Peng-Robinson equation. I didn't bother writing that in here. You can look these things up. There's also, you can look them up for other equations of state also. But the key thing that I really think that is important for you to notice is that now they introduce how to do mixing rules for these equations of state. They're all going to be a little different, but kind of similar ideas. So this is the Peng-Robinson equation. Okay, it doesn't look any different than it did before. It's just that the A and the B are not for a pure substance, they're for the mixture. I get these by estimating using pure properties and some combined property data. B sub I is just simply B for the pure substance. A sub II would be for pure species I. A for IJ is for I mixed in with species J. I can estimate A sub ij using this mixing rule, which says that I'm going to take the pure component A's, the square root of their product, a geometric average, times 1 minus the binary interaction parameter. And this quantity is going to be Aij or Aji. There's no difference based on order. Now, the binary interaction parameters would typically be based on experimental data, something like that. This is a partial table of what these values are. In many cases, you're going to see that there's nothing there. Since the order doesn't matter, they don't put anything on the bottom half of this table. So the top triangle, in other cases, they have a blank there. A blank does not necessarily imply 0, but it does mean that you don't have a value available to you, okay? And you should probably, maybe from experimental data, something, you're going to need to come up with what those estimates are. Now, we've been using this in Aspen, and when we do this in Aspen, they have binary interaction parameters for most of our things entered in. We've been just saying, oh, accept whatever they have, but there are times when they either have nothing or they have a value that is not very reflective of the binary interaction under your conditions. And so you may need to go through and edit those based on updated information. Liquids, how it can be done in a couple of ways. Sometimes we can actually use an equation of state. Unfortunately, equations of state tend to not describe liquids very well. So we instead often use an activity coefficient model. Now, the activity coefficient model says I'm going to take x times the pure liquid fugacity and then multiply that by gamma, where gamma is the activity coefficient. If I actually wrote out the math for this and the math for this, what I would see is the missing piece says that the natural log of gamma is the partial molar excess Gibbs energy for the species I divided by RT. Now, we're going to come back to this in the next lesson, but this is going to be how we're going to typically approach liquid fugacities. Finally, let's look briefly at solids. Most solid mixtures are really just different pure crystals that are kind of blended together. They may be in some sort of crystalline form. In fact, just this week, someone announced a discovery of ice 7 locked into a diamond crystal structure. But they're very separate materials. In that case, I can estimate the fugacity of the solid for that species in a mixture as just the pure fugacity for that solid. But if you have a solid solution, so for instance, instead of just, using iron, okay, for cast iron, we start adding extra chemicals to it and we make steel or stainless steel. Those solid solutions are much more complex in how we can estimate their fugacity. We will not have time to cover that in this course, but if you have the textbook, Chapter 12 of Sandler's book, does a fairly nice job of covering those, and you can read about those as you need them. So in our next lesson, we're going to come back and look at activity coefficients and what models we can use to estimate those liquid activity coefficients. Thank you very much.